The accumulation of heavy metals in agricultural land has a negative impact on soil ecosystems and poses a significant health risk to the public. Crops such as rice that are planted in submerged conditions are even more exposed to heavy metal sources from both soil and water. In fact, rice is also the second most consumed crop in the world and is likely to expose the majority of its consumers to heavy metals.
Moving to the study case, this study has received the samples data from the Food Quality and Security Division of the Gombak District Health Office, which consist of the rice types, rice brands, and heavy metals, like arsenic, cadmium, copper, selenium, chromium, cobalt, nickel, and iron contained in the rice. This study was carried out to determine the hazard index in the various types of rice and brands and to determine which elements have the highest contribution towards the hazard index, focusing on 3 elements, which are arsenic, chromium, and cadmium.
In methodology part, we calculate the hazard index. It is used to determine the overall potential risk by the elements. The hazard index can be calculated by using the formula which shown in the first row. To get the hazard quotient, the second equation is used, which EDI, estimated daily intake, divide with TDI, tolerable daily intake. Then EDI can be calculated by using the third equation, whereas TDI are calculated by the fourth equation. PPY is the provisional tolerable weekly intake suggested by the Joint FAO-WHO Expert Committee on Food Additives. Tomb analysis are used to analyze the data. For Objective 1, one-way ANOVA is used to determine whether there are any statistically significant differences between brand. Then, to achieve Objective 2, multiple linear regression is used.
So next, this is the result obtained throughout this assignment. First, there will be hazard indexes for various types of rice and brands ranging from brown rice 1 to glutinous rice 3. One-way ANOVA is used to determine whether there are any statistically significant differences between the means of 2 or more independent unrelated groups. From the ANOVA table, the significance value is 0.000, which is below 0.05. Thus, we reject the null hypothesis. Therefore, there is a statistically significant difference in the hazard index between different brands of rice. Then, the post hoc test can be used to determine which of these groups differ from each other. From the multiple comparison table post hoc test, it has revealed that the risk of each type of rice and brands is ranked in the order of brown rice, white rice, fragrant rice, basmati rice, and glutinous rice, which has the smallest risk. After that, we can choose 3 elements, which are arsenic, chromium, and cadmium, to test their correlation with hazard index. First, we obtain the descriptive table of these 3 elements. Then we run the multiple linear regression to predict the outcome of a dependent variable. From the interpretation of the model summary, R squared is 1. When expressing it in percentage, it means that our model explains 100% of the variance in the hazard index. In addition, from the correlation table, the element of arsenic correlates very well with a hazard index with the correlation coefficient of 0.999, which indicates strong positive correlation, while the other variables, cadmium and chromium, show a correlation of 0.181 and 0.250 respectively. This has proven that there is a weak correlation with the hazard index. In order to assess the statistical significance of the result, we interpret the result labeled ANOVA. As the model in this example reaches statistical significance, we reject the null hypothesis. There is significant prediction of the hazard index by arsenic, chromium, and cadmium. Lastly, by referring to the output box called coefficient, we are able to know which of the elements included in the model has contributed to the prediction of the hazard index. In this study, the tolerance values for each variable are 0.922, 0.973, and 0.947. All of the values are not less than 0.10. Therefore, the data do not violate the multicollinearity assumption. This is also supported by the VIF value, which is 1.084, 1.028, and 1.056, which is well below the cutoff of 10. The largest beta coefficient is 299.314, which is for arsenic. It is followed by chromium with a beta coefficient of 6.713 and cadmium with 5.722. Therefore, the contribution of arsenic is larger than chromium, while chromium is larger than cadmium. Besides, from the normal probability plot, the points lie in a reasonably straight diagonal line from the bottom left to top right. This would suggest that there are no major deviations from normality. In addition, outliers also can be checked by inspecting Mahalanobis distances. Maximum value from Mahalanobis distance shows a value of 13.358, which does not exceed the critical value. The presence of the outliers can also be detected from scatterplot. Several outliers are observed. A few outliers are accepted, as it is not necessary to take any action towards a few outliers.
As a conclusion from the hazard index, arsenic, chromium, and cadmium have a significant difference. As a whole, a Tukey post hoc revealed that the risk of each type of rice and brands is ranked in the descending order of brown rice, white rice, fragrant rice, basmati, and lastly glutinous rice. Arsenic has been found to have the largest beta coefficient, which is about 299. This means that this variable makes the strongest unique contribution to explain the hazard index, when the variance explained by all other variables in the model is controlled for. These findings may assist Food Quality and Security Division to redefine the types of rice available at market and negative impact to human health.
We would like to express our special thanks of gratitude to our lecturer, Dr. Louis Lejuman, for giving us this opportunity to learn more on this course and giving us support and understanding during the project timeline. We would like to thank her for the guidance that needed in completing this coursework. Last but not least, this assignment could not have been done without the effort and cooperation of our directors of Food Quality and Security Division, Nirul Siazwani, Assistant Director, Nursimimi, and their group's members, which are the Data Group, Report Group, and Video Group. Without synergetic collaboration from each one of us, this coursework may not be completed within the planned timeline.